that slope, greater than that slope, greater than the slopes as you move towards, the tip of the fin. Does this make sense? All right. Now, obviously, in order to answer this question, we need to find how t is going to vary with x. Because if we know that, then we go to this equation, we get our flux at the base. In other words, we get the flux here. In other words, we get negative k dt dx at x is equal to capital L, because that's the base. And what do we do to that in order to get calories per second? Gabriel? Look. In order to answer that question, we want to answer that question. What do we do?
To that?
Yeah. Make it yellow. No. We do something to it. Jasmine? Yes. Thank you. In other words, you see this yellow area here? If that's the flux, which is calories per second per centimeter squared, if you multiply by this area, you're going to get the answer to the problem. Understood? All right. So we need to do that, which means we need to get a differential equation with boundary conditions, solve, and get the answer to the problem. Now, how do we get that differential equation? In order to make it a little bit simpler, we're going to make this kind of cylindrical in order to see to visualize very well the system for which we're going to write the first law of thermodynamics, okay, which is an energy balance. So, before I do that, I will show you on this. I did not bring this here, but since it's here, I'm going to use it. So, the element onto which we're going to write a balance is going to be a slice, a very thin slice of this, that goes all around like this. Do you see it? That was cut it out, cut this. And then make a balance, heat goes in, minus heat goes out, due to conduction, minus heat that goes out due to, Jasmine? Okay, let me repeat. Heat that goes in due to conduction, heat that goes out due to conduction, minus heat that goes out, blank, blank, blank. Will? Caitlin? Nah? Is that a question mark or exclamation? Exclamation? Well, you should put exclamation. It's due to convection. So please look at this, right? We take this little element out. If this were cylindrical, this element would be like what? Like a coin, right? Like a quarter. Standing. So, do you have a quarter or any coin? I don't have any. Thank you.
It's Canadian.
Oh wow. Okay.
See you better grade.
All right. Going to give him the grade that this guy's on it. And I gave him 1 out of it.
It's 100 cents. So.
Okay, so remember, this is like a stack of coins, right? That goes all the way in order to make a fin. So there's going to be heat due to conduction, perpendicular crossing this surface, in, minus out, both of them due to conduction. And then there's going to be heat, which is actually, that's why this works, because of the heat that is leaving what I'm touching right now. Or in this geometry, where the red is, the red area. And that's due to convection, because we said that Newton's law of cooling is convection. In other words, the heat that is leaving the rim of the coin, or this area that I have painted red, is going from solid to fluid. Therefore, it is convection. Therefore, it is Newton's law of cooling. Okay? Okay. I was gonna swap. All right. So now we're going to draw that coin like this. And because we want to write a balance for increasing x, the way that I have drawn this way is x is 0 here, but actually, so the way that I have drawn it here, it would be something like this. This would be the area. So this place here would be x is equal to 0. This would be x. No, I'm sorry, x. This would be x. This would be x plus delta x. This position. The thickness is, of course, delta x. This is x. This is x plus delta x. Even though I know that physically heat is going the way I have drawn this from left to right, it's going this way, I want to write the balance in the direction of increasing x. Therefore, it's going to be heat due to conduction. So it's going to be Q times the area at x minus Q times the area at x plus delta x minus the heat that we're losing to the surrounding because of convection, and Newton's law of cooling, which will be H times the temperature of the fin, which is the same at all positions in the cross section, and therefore it's the same on the wall of the fin, right? So it's going to be the temperature of the fin minus the temperature of the fluid, and this is going to be equal to 0 if we have steady state. Remember, there is no work. We only have heat flows into this system. Okay? In other words, we could have done this also with material energy balances before we knew first law of thermodynamics. Just having the heat that goes in minus the heat that goes out, since there is no work. Okay? In other words, heat that goes in comes this way, somewhere on this surface, and then it goes out from that surface. This would be Q at x. This would be Q at x plus delta x. Now, notice that these Q's are multiplied by the area, the cross-sectional area. So, in order to get here calories per second, this is flux. It has to be multiplied by the area. Ninghao, what do I have to write for the area?
L times.
No, you want this area, the area of the red. This.
Delta x.
Delta x times.
P.
Very good. So do you see what he said? delta x times P. You understand that, right? So it's delta x times P. P times delta x. So that's our equation, differential equation. Not yet, difference equation. We'll turn it next to differential equation. First, we write this as q at x plus delta x minus q at x plus ph over a times t minus tf is equal to 0, dividing of course this by delta x. And then take the limit as delta x goes to 0. Which will give us dq dx plus ph over a t minus tf equals 0. Then we're going to substitute for q by means of Fourier's law. Fourier's law substituted in this shall give us d squared temperature dx squared minus ph over k a times t minus t sub f being equal to 0. And now this is a second order differential equation with conditions that at x is equal to 0 and at x is equal to L. Let's start with the easy one. Caitlin, at x is equal to L, what is the temperature? Very good. So at x is equal to capital L, t is equal to t sub b. Now take a stab for the first one. X is equal to 0, which is the tip of the fin. What do we write? Yes.
T is equal to TF.
I said before that we cannot do that. When we touch it, remember, it's hotter than here. It may not burn as much as we touch there or here, but okay, so yes.
dt dl is equal to 0?
dTd?
dt over dx is equal to 0?
Yes. Very good. Very good. But let us kind of like derive that. We're going to derive why that is so. So actually, to write, so this is the hardest part of today's lecture. If you don't pay attention, if you did not pay attention before and you still understood, you will not understand now. Pay a lot of attention. This is the tip, right? What we're going to say is, if there is, I'm painting it yellow. What comes out of this yellow surface as heat goes where? To the environment. Okay? So we're going to write the following for the tip. We're going to write that k dt dx at x is equal to 0, which is the tip, times the area, is equal to ht at x is equal to 0 minus t sub f times the same area. Right? Which means that the A's, of course, can come out and be erased. We're saying that the flux due to conduction, like the yellow tip, the flux out of here, which is the derivative dt dx right here times k with a negative sign is equal to the flux due to convection. Does it make sense? And then after we have said that, we're going to say the following. We're going to say, well, yeah, there is some, and actually if I'm going to redraw the profile, this slope here is going to be non-zero, because what he told us is to say that this slope is equal to what? To
0.
to 0, right? In actuality, this slope is going to be non-zero, but look, the slope becomes smaller, 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 absolute value of the slope. And it almost becomes 0. And it is much less significant than all the other slopes. And it only happens at one point. So even though in reality the slope will not be 0, it will be almost 0. And when people did the equations and they did the numerical, they ended up getting numbers. The numbers showed very small error if we make that assumption that he made. So we're going to make the assumption that at x is equal to 0, dt dx is equal to 0. This assumption is known as the insulation assumption, because it is the same thing as saying that this tip is insulated. It is the same, in other words, as if this thing at the end had some material on it that is totally thermally non-conductive, bless you, and does not let any heat go out, which means it's insulated, right? So this yellow thing, you could see it as an insulation material. They have put here. That's why we call that condition an insulation condition. Do you understand everything until here? Because I have to remove stuff to make room for other. Okay. Now the next thing that we're going to do for this problem is to non-dimensionalize okay? Just like we have done before, 3 months ago, non-dimensionalizing stuff, we're going to, the obvious thing is the side, right? Being x over L, defined as x over L. Which means that when we are going to divide this by capital L squared in order to make it side, if I divide this part by capital L squared, it's the same as multiplying this by capital L squared. I have not changed anything. So this now has become a second derivative with respect to psi on the left. We have d psi minus Alexis. What are the units of this group? Fast. Think fast. Steph.
Of the second one?
Yeah, the whole circle. What are the units of that? Gabrielle. What?
Meters squared.
Dominic.
1 over meters times Kelvin.
Alex.
Non-dimensional.
Dimensionless, right? Very good. Do you see why? Because what are the dimensions of this group here? Temperature. What are the dimensions of this whole group? Temperature. So this has to be dimensionless. And this whole group, we are going to define it as the Greek letter beta to the square power, and you'll see why we put the square later. And it has a name which I will give you next time. Or maybe I can give you today. pH over Ka times L squared. This is a very important. Actually, beta is known as the Beal modulus in heat transfer. But this is beta squared, it's not beta. Okay, the Beal modulus. So it's not biot, Beal. It's spelled biot, it's spelled B-I-O-T. Beal modulus. So I'm going to put here my beta squared, and then I'm going to have T minus TF equals 0. Now I'm going to, yes,
Isn't it still d squared t? Yeah.
thank you. Very good. Very good. Those are the things I do need to see if you're following, right? Those mistakes. You believe it? You're gullible. You believe it. Okay. So now we have to non-dimensionalize by temperature. Now remember, this we have a T minus TF, and TF is a constant, which means that we have, first of all, we have two, the next few sentences are something that I'm giving you the reasoning on how, bless you, how to non-dimensionalize something you should encounter in several courses to follow, and then as engineers. So what is the logic for non-dimensionalizing temperature? We're going to observe that we have two constant temperatures. We have TB and we have TF. So like the simplest, most naive way would be, well, divide by TB or TF. Okay, but then you have like lots of constants that you're carrying around. Why not divide by both of them? In fact, why not divide by the difference of them? Because we do have, are you paying attention now for the logic that we're using? There's a difference here in temperature. And this is kind of a reference temperature because it's a constant temperature. So what if we defined a temperature that actually had a dimensionless temperature that had a minus T sub F? Can we do that here? And what happens when we put right here minus T sub F? What have we changed in the equation when we have done that? Down. What have we changed?
Nothing.
Nothing, right? Because it's a constant. So that's great. That's what we should be doing. Because we have minus TF here, minus TF here. And then, since we have that, what does it make sense to divide both by? What?
T minus TF
T?
minus TF.
Well, T is a variable. How about TB minus TF? Right? TB minus TF. TB minus TF. Which means that our theta, dimensionless temperature, should be T minus TF divided by TB minus TF. Okay?
What is H?
Heat transfer coefficient. Okay? Heat transfer coefficient. That's H. And I understand you have organic test. But I did say last time that if you knew what we did last time, this would be much more enjoyable, right? And it's a cumulative effect of what you grasp during class. Yes.
Have we gotten to the reason that we made the x-axis start on the right
No.
yet? No? Okay.
No, that will come with the mathematics.
Okay.
Yes. Okay. All right. So do you understand all this? So now we have d squared theta d psi squared minus beta squared theta equals 0, and at psi equals 0, d theta d psi, which many times the first derivative in in mathematical notation becomes the subscripts of the. Have you seen that before? Have you seen the, using this notation for first derivative of theta with respect to psi? Who has seen that? You've seen it? You've seen it? Yeah, you've seen it, right? So this means first derivative of theta with respect to psi. And then at psi equals to 1, because when x is equal to 12, so psi is equal to 1. Patrick, what is the condition? Theta is what? Is it 1?
Yes.
Okay. So he says it's equal to 1 because, thank you, because if you subtract from this TF and you divide by TB minus TF, you get 1. So that's very good. Theta is equal to 1. And now we have a differential equation which is relatively easy to solve. Have you solved this equation before? Dominic? Yes or no, I want. Have you solved this equation before? Nehal? Steph? Have you solved it before, like in a course, in any course? Do you remember?
Yeah.
In which course?
Calculus.
Which calculus? Okay,
3.
Alex, have you solved this equation before? Patrick? Okay? Okay, so here is, again, another thing that I have said. I did not learn these things just from holy inspiration, right? I learned it by teaching, right? Because I saw students not seeing it. So have you seen it before?
Yeah.
Now, when I'm gonna put this equation differently, you would, everybody will say, oh yes, I have seen it.
Yeah, I think
It's diffuse. Yeah, it's anywhere.
How many times have you done this? Never?
Yeah, never.
Steph?
Never.
Never?
Did we do that? Did we do that in
No.
this class?
FAQ.
Oh, okay. I'm not in that.
Yeah.
So
In-
make it happen.
Okay, in DiffQ, you haven't taken DiffQ yet?
No.
Are you in DiffQ now?
No.
Oh, thank you. Thank you. I mean, anybody else who has not taken DiffQ?
Great.
All right, okay, so she's the only one, like, who had a real reason to say that I have not seen it before, or maybe I have seen it. But everybody has seen it. In fact, if you could not do that in DiffQ, what was the chance of passing that course? Probably 0, right? Now, in DiffQ, okay, so I'm going to be reviewing, since not only for Steph, I think there's one more student who's not here today, who is not enrolled in DiffQ right now. So I'm going to repeat things, but in a way that probably, even though we're not, who knows this stuff, but perhaps not exactly the way I'm going to present it, might learn something, okay? So please bear with me. When we have an equation like this, DiffQ tells us there is a cookbook method that says you set up the so-called characteristic equation. Wherever you have a double derivative, you put a capital D to the square power. Where you have other derivatives, because you would have the first derivative, but you don't in this case, right? You just have the 0th derivative. You put d to the 0 power. So this, and then this is an algebraic equation. So Steph, this is just a cookbook. I'm not going to explain that. Okay? When you take DFQ, you will understand it. Okay? But that's what you do. That's the result of it.
Wait, why did you
The-
make
the-
it from Y?
Okay, so this is second derivative. This becomes just this new thing, D cookbook, right? It's like a cup of sugar, right? Why it's a cup of sugar? You don't. Yeah.
Oh, it's just like a thing.
Yeah, it's just a
That
thing.
makes sense.
So I just want you to understand, to accept this, not to understand it. Okay? To accept it, right? So you have d squared, because this is a second derivative. You have minus a, you have d to the 0 power, because this is which derivative? Zero derivative. It's not first derivative, zero derivative. So you have d squared minus a is equal to 0. And this has roots, d is equal to plus minus square root of a. And then the answer is that y is equal to some integration constant c1 e to this root square root of a x if y is a function of x, right? Y is a function of x. So that's the independent variable plus a different integration constant e to the negative square root of a x. Okay? So, do you accept it? All I'm asking you is to accept it. Do you understand that this is like, okay, that's how you do it? You take the sugar, you mix it up with water, and then something nice comes out.
Yeah.
With the flavor, you know, other stuff. You get your cookie or whatever. Right? It's not like why. We don't explain why.
Sugar.
Just
water,
this is how you do
basic.
it. Is everybody on board with this? Is everybody okay? Now, what some of you also learned is that this is totally equivalent to writing this as C1 prime sinh square root of ax plus C2 prime, integration constants, C1 prime, C2 prime, cos, hyperbolic cos of square root of ax.
I've never seen Censure Kosh before.
Okay,
Oh, hyperbolic sign.
okay, who has seen it?
Look, I've never seen this, but I've seen the hyperbolic sign.
Okay,
I have.
who has seen this? You've seen this. Okay. You don't have to have seen it. Because what will happen now in the next, so that means that even those of you who have not seen it, who get like straight A's, if you have not seen it, because depending on who you had for calculus, so he probably had a different teacher or he saw it somewhere in physics, in a physics course, you are going to learn stuff about calculus and functions that, if maybe I'm saying too much about it, it's going to be pretty revealing what I'm going to show you, right? Okay? So, you don't have to, you are going to understand this next, okay? Most of the stuff that you have learned in calculus can start from a function that describes a lot of natural phenomena. And that function is called the exponential function. You've heard that, right? E to the x. Most of the time it's e to the minus x, but e to the x is exponential growth, e to the minus x is exponential decay. E to the x, there is an infinite series for e to the x that does not take any good memory to remember it. Who remembers this? Yes, tell me.
Is it 1 plus x
Very good. Over 2 factorial
Right.
plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus x to the fifth over 5 factorial plus x to the sixth. There's a reason why I'm putting so many. Plus, and it keeps going, right? Now, have you seen this before? Okay, now we're going to pretend that we are the ones who are going to like define new functions, and we say we're great mathematicians and we want to do the following, bless you, on this function, to split it into the series of the even powers plus the series of the odd powers. So we're going to write this as 1 plus x squared over 2 factorial plus x to the fourth over 4 factorial plus higher order terms plus x squared x to the third over 3 factorial plus x to the fifth over 5 factorial plus higher order terms. And we're going to call this function cos or hyperbolic cosine of x, and we're going to call this function sinh of x. Now, graph-wise, e to the x versus x starts at what number when x is equal to 0? At 1. And grows exponentially like this. So this is e to the x. Sinh plus cos should add up to e to the x. So the cos starts at 1. But of course it's smaller. And the sinh starts at 0. Because all the terms have some x in it. And it goes like this. And if you add this with this, in other words, this should equal that, right? This should be equal that. If I have drawn it correctly, this should equal that. Because red plus yellow makes white, in this case.
It's a good thing you're not an art teacher.
Yes, not acceptable. I could have used orange for this. Alright. So do you understand now what cos and sinh are? Now, one more thing. I want, because in our equation we have a derivative, right? Remember that derivative that we have? So we want to know what the derivative of cos is and what the derivative of sinh is. Look at this. When we take the derivative of this, what do we get? 0. Right? The first term, 1. When we take the derivative of this is 2x over 2, it's what? X. So we get the first term of that. See that? When we go now here, that's why I have kept these terms. 4 times x to the third divided by 4 factorial. 4 factorial is 4 times 3 times 2 times 1. It's 4 times 3 factorial. So when we take the derivative of this, we get this. Do you see that? So the derivative, therefore, of cos x prime is sinh x. Right? So we prove this way. Okay? Then we're going to prove something kind of cooler that you can relate to. Now the derivative of sinh is what?
Cosh minus 1.
Because the derivative of x is 1. The derivative of x to the third over 3 factorial is x squared over 2 factorial. The derivative of x to the fifth over 5 factorial. Therefore, right, all of this you have to know by heart, right? For next time and for the exam, right? Needless to say. And you know, don't feel bad because as you saw they hadn't learned this part, right? That's all that was new to them. Everything else is you're on the same boat. Okay, so they don't have an advantage. Sinh x prime is equal, of course, to cos x. Alright? Now, notice that we can come now to this equation. Pay attention, I'm going to erase this because you did not know it. One more thing we're going to do. Since, and I'm going to do it in this area here. Since e to the x is equal to cos plus sinh of x, e to the negative x is equal to what? No. No, that's not the way you do it. Please pay attention. If I come here and I put negative sign, okay? So I'm gonna put a pink negative sign. Oh, that's scary. Pink negative sign there. This will become negative, right?
Right, yeah.
But this one will stay positive. This will become negative, right? But this one will stay positive. Do you get that? This one will become negative, right? But this will stay positive. Which means it's going to be positive, negative, and so on. Which means
Cosine
that
plus
what we have proven is that e to the negative x is equal to cos x minus sinh x. And e to the x plus plus e to the minus x over 2 is going to be just cos of x. And e to the x minus e to the minus x over 2 will be equal to sinh of x. Alright? See that? Okay, so let's continue up here now. We're going to write this as C1 e to the square root of a x. But I want to write this in terms of cos and sinh. Cos and sinh. So I want to write that this is times cos x plus sinh x plus C2 cos x minus sinh x. Yes.
What the square root of a?
A, yeah. Square root of a. Thank you very much. Square root of a. Square root of a. Square root of a. Okay? Then we're going to factor to isolate the causes and the secants, and we shall have this is equal to C1 plus C2 times cos square root of a x plus C1 minus C2 sinh square root of a x. And now I have proven what I told you before. In other words, that this is just another integration constant, C1 prime, and this is C2 prime. Okay? Do you have questions about all this? Now, I'm gonna do something more interesting now. Maybe we should wait for Alex. There he is. Yes, I was going to wait for you. This part you can get from somebody else, but this is something. Okay, now pay a lot of attention. You know nothing about trigonometric functions. Zero. Nothing. Right? Imagine. But you do know the imaginary number, which is I, small I. So what we're going to do is, we're going to stick a little I here, e to the ix. ix squared, ix to the third, ix to the fourth, ix to the fifth, ix to the sixth. In other words, we take that infinite series for the exponential, and in the argument of the exponential we put a 9. And then what we see here is that and we still want to divide up the series into even powers, odd powers. However, the difference here is going to be that now the first term will be this for the first series, but the second term will be ix squared, which means that here we're going to have what? Negative. See that? No? I squared is -1? No?
Oh, okay.
Okay?
Yeah.
Okay? So that's going to give us the negative sign. Then we're going to come to the I to the fourth. You see that? I to the fourth is positive 1, because I times I times I times I times I 4 times, right? I, not 4 times I, but I to the 4 is positive 1. So this is going to be actually positive, like before. But the next one, to the 6th, will be what? Negative. See that? And then for this, the first term, we're going to factor out an I out of the entire series, because every part is going to have an I. So the first term is going to be I times, of course, x, right? The next one is going to be I factored out times I squared, which will give us here negative sign. But the next will be I times I to the 4th, and I to the 4th is positive, so we still keep this. But the next one will be negative. Okay? So we see how we have this series, and nobody told us about sine and cosine, so we call this series cosine of x, and we call this series sine of x. And in fact, these are the infinite series for, I'm sure you have seen the series, right? But this is the proof that these are the series. Because, not the proof, it's more like we define them from the exponential, because remember, the exponential governs the world, right? Literally, as a function. You have, like, which function describes physical phenomena? One. If you have to name one, it's not linearity. Linearity means absence of life, absence of, like, you know, everything is like boring. Okay? But things that describe the world are hidden in the exponential function, which of course includes sine and cosine. sunrise, sunset, sunrise, right? Sine and cosine, periodicity. Okay, all this is within the exponential function. So now, the biggest mistake students have made in the test is the derivative of cosine. They were pounded so much since high school. What is the derivative of cosine? Negative sine. So when we do this, they make that mistake. This is positive. But of course, if we look at this series, we'll see how it is negative, because what is the derivative of 1? 0. What is the derivative of negative x squared over 2 factorial? Negative x. It's the negative of this. What is the derivative of positive x to the 4th over 4 factorial? It is? Right. So we can see how we obtain that equation, that the prime, or the first derivative of cosine, is actually negative sine, right? But that's not true for cos, or hyperbolic cosine, right? That's positive, the derivative. However, if we do the contrary here, like go to the sine infinite series, what is the derivative of x? 1. What is the derivative of negative x to the 3rd over 3 factorial? It's negative. So we get exactly, right, that the derivative of sine is actually positive cosine. Okay? Yes?
So it's where sine or cosine was derived from?
No.
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 Just
We could have derived. They could have been derived this way.
But they're derived as this.
Right. Right. They were derived and defined with a unit circle, like what you probably did like back in pre-calc or trigonometry or something. Yeah. So that's how they started. But they could have been done this way, and everything could have been built based on this, based on the infinite series for the exponential. Okay. All right. This was the parenthesis. Now we're going to go to our problem.
One thing.
All right, so we had our differential equation as, please, I do this on purpose, and I may do it during the exam. Theta psi meaning second derivative of theta with respect to psi, minus beta squared theta is equal to 0 with conditions. At psi equals 0, theta psi is 0, and at psi equals 1, theta equals to 1. And we're going to choose to use the sinh and cos, c prime times cos plus c2 times sinh, right, for our constants. So theta will be c1, some integration constant, times cos of something, plus c2 times sinh of something. Please think very hard and tell me right away, Minhao, what is that something? Cos of what? Oh, the cos has to have an argument, right? Look at it here. It's all here. Steph?
Square root
Of A?
times
But I don't have A. Here I have A, there I have beta squared.
square root of beta squared theta.
So square root of beta squared is what?
Theta.
Beta. So it's beta. That's why I defined it, in fact, as somewhere here it was as beta squared, in order not to have square roots. Okay? So beta, and what does it multiply the beta? Step. First. X, but we don't have X. What do we have instead of X?
Psi.
Very good. beta psi. Okay? Beta psi. That's it. Because our independent variable is the dimensionless x, which is psi. Now, let us get theta psi. Theta psi, Alexis, is what?
Beta times C1
C1 times beta, thank you.
cos.
No,
Cosine is
sinh beta psi plus C2 beta cos beta psi. And of course, the reason you put the beta is because you know that when you do sine ax prime is equal to a cos, right? You take the derivative of the argument. That's another mistake that many times students will make. You see that? Okay. So now we're going to apply that to 0. So this is 0 when psi is 0. So we have C1 beta sinh of 0 plus C2 beta cos of 0. And I'm going to claim that one of these constants is going to go to 0. Patrick, which constant will go to 0 because of this boundary condition? C1 or C2? Very good. So he says sinh of 0 is 0, right? Sinh of 0 is 0. But cos of 0 is 1. So what multiplies that has to be 0. Therefore, C2 is equal to 0 because of this boundary condition. And then we're going to use the first boundary condition that says theta is equal to 1 when psi is equal to 1. So we have C1 times cos of beta, or C1 is equal to 1 over cos of beta. Therefore, the answer is theta is equal to cos beta psi over cos beta.
So is C2 0 in that equation because
Okay.
it has to equal 0, or do you know
Because
it's
that,
zero?
yes, that's how you find the integration constants of differential equations. And remember, I'm not going to ask anything past this, right, in terms of finding constants. So you use this, the first boundary condition that says at psi 0, theta psi, meaning the first derivative is 0. So you set the theta psi 0, and you plug it into psi 0. Sinh of 0 is 0. But cos of 0 is not 0, it's just 1. So you cannot have 0 equals constant times something that is not 0. The constant has to be equal to 0. I mean, that's how you find integration of constants in differential equations. Okay? So now we have the answer, right? And you can get the engineering answer because you can plug in T minus TF over TB minus TF for the left hand side and all the other constants so that you have X instead of psi, and you can get the derivative because of course you know that the derivative of course is sinh. And you can answer now, we have answered the problem that we set out to answer. You remember the engineering question was, how much heat is leaving the wall? Okay, a few more minutes I'm going to give you here. Yeah. Now, when you read, which you must, when you read this problem in the notes that I have given, there are going to be some changes. One change is that instead of having a random cross-sectional area, a random cross-section with a perimeter P, they will give you this, a rectangle, a certain distance here and a certain distance there, right? That's one difference. The other difference is that the origin is not taken at the tip, it's taken at the base. And you will see why we chose it at the tip, because the algebra is much, much easier if you choose it at the tip. Because at the tip, you have 0 and 0, and that makes one of the constants immediately go to 0. When you do it the way that's done in the notes, and by the way, all books do it that way, not this way, you will see that you will have many more steps, and you will have to even have some equation between cos and sinh that you may or may not understand. Okay, all this like studying projects. If you don't study, I cannot answer your questions, right? You will not have questions. One. And then, just like I did in previous homework, I pull out a problem straight out of the packet or homework problem, then I give it, then you don't do it, then you're upset, but you cannot say I did not tell you it was gonna happen, right? I'm telling you it may happen, right? So do you understand that? Yes. So you have to understand perfectly what's there in the notes and why this is simpler. This also makes you understand cos and sinh.
So in the notes, they solve for 1 minus theta, or would it be equivalent?
No, they solve for theta. You will see. You will see. No, theta is defined exactly the same way. It's psi that's defined differently. And they call it 1 minus zeta at the end to make it. In the end, it goes it's exactly the same answer. Then, another thing that they do, and I absolutely want you to also do, and I consider it kind of silly, and I cannot believe that other books that follow this problem also do it the same way. And these are the smartest people who are infinitely smarter than I would ever be. But it's kind of silly what they have done in this problem, because when they ask the engineering question, they have this stack on the surface. They ask the engineering question, how much heat is being released to the surroundings? What they do is they say, well, how much heat is released out of this red thing? And then integrate from here to there. And be sure to do it that way. But they are missing out that actually that heat that is lost out of this whole thing is coming out of where? Of this base, right? In other words, if at steady state this whole thing is losing 155 calories per second to the surroundings, how much heat is coming through here? Same, right? And mathematically it's much easier to do this than to do the other one, right? But tackle it, okay? Tackle it. So do you understand what the homework is for next time? Of course, cos and sinh, and tell those who were not here, you have to have them like on your fingertips for next week and the exam week. Hint, yes.
So what's the reason that we put x equals 0 at the tip?
You will see it when you do the other way.
Okay, it's for the other way.
Yes.
Okay.
So let me give you one more homework in order to understand this better. Try to solve the problem with the exponentials. Number one, do you hear me? Try to solve the problem with the exponentials. If you do, it will be much, much more work. And in the end, you will have to define sinh and cos. So you can also do that. That's not done in the notes that I have given you. If you take the tip, okay, we still have 2 more minutes. If you take the tip at 0, at L, at 1, at the tip, at size equal to 1, In other words, these two things are going to be inverted. You're going to have theta psi is equal to 0 at 1. And when you set this 1, 1, 1, you're going to have none of the two constants is going to drop out. Then you're going to have more algebra. Same thing when you have this at 0. Theta is equal to 1 at 0. You're going to have for this equation 1, but this will be beta, and this will be also beta. So you're going to be doing that as homework, right? Instead, if you pick the tip where the derivative is equal to 0, and you start from there, then you have at 0, something is 0. And that gets you rid of an integration constant right away. Makes it much easier. Okay? But be sure you understand everything in the notes about this problem. And of course, this is the more important part, right? To understand what we have done here, but also understand that. Okay?